Now let's move to Mendelian genetics. This is a stamp from Austria, which is honoring the 100th anniversary of Gregor Mendel, the discoverer of the laws of inheritance. He was an Austrian monk. He studied sweet peas, and he studied 10,000 plants, 22 varieties of peas, and he wrote a paper that was unrecognized for 35 years after his death. He came up with the laws governing Mendelian genetics. Let's look at that. This is our case. By the way, I wrote these cases trying to incorporate the key features of these topics that you may see on the exam. So I think it's well worth your time to examine these cases in detail. We have a 23-year-old black prima gravida who was 12 weeks gestation, first trimester. She has been diagnosed with sickle cell trait. Sickle cell trait has hemoglobin A and hemoglobin S. Her husband and father of the baby is also AS, or sickle cell trait. What is the risk of her baby having sickle cell disease, SS? Okay, this is in your notes, and it looks at the various pedigrees of the Mendelian disorders. We have autosomal dominant, we have autosomal recessive, X-linked dominant, and this is the X-linked recessive. And we're going to go through each one of these in order. The squares are males, the circles are females. If the circle or square is solid, it is an affected person. If there is an X through it, it means that they are carriers, unaffected but heterozygous, and double lines mean consanguinity, which is closeness of genetics. So let's go through each of these. We'll start out with autosomal dominant. Autosomal dominant is the most common Mendelian defect, and here we have the pedigree. What should you look for? Number one, does the disorder skip any generations? And the answer is no. It's in every generation. Second question, are there any carrier states with the X's? There are no X's, so it does not have any carrier states. The third question is, does it affect both males and females? The answer is yes. That must be an autosomal dominant. Examples of that: achondroplastic dwarfism, Marfan syndrome, certain kinds of polycystic kidneys. These tend to be anatomic disorders. Now, it's well worth saying that the majority of achondroplastic dwarfs are actually new mutations. But if they are genetically caused, they will result in autosomal dominant disorders. If you think autosomal dominant, think anatomic disorders. They're transmitted by both genders. All generations are affected. No carrier states. This is what I call a triad. Three things together which are only accountable by one diagnosis, and that is autosomal dominant disorders. Now we move to autosomal recessive, and you see how these are different. Autosomal recessive, does it skip generations? Yes, it does. It is not present in this generation, at least the disorder isn't, but it is down here. Are there carrier states? Yes, there are. There are far more carriers than there are affected individuals. Are there differences in gender? And you can see the carriers can be both male and female. And can you see this double line between the male and the female? The closer the genetics for both parents, the higher the likelihood of having an autosomal recessive disorder. It is estimated that each of us have half a dozen lethal autosomal recessive disorders. And because our society frowns on mating between closely related individuals, we don't see these types of disorders very often. In cases where there is consanguinity, we see increased findings of autosomal disorders. Now you notice if both parents are carriers, we're going to have 25% of the children will be affected. 25% will be neither affected nor carriers, and 50% will be carriers unaffected. Examples of these is what I call the alphabet soup. CF, cystic fibrosis; SC, sickle cell disease; TS is Tay-Sachs disease; PKU is phenylketonuria; and CAH is congenital adrenal hyperplasia. Notice these are all enzyme disorders. If they're anatomic disorders, you think autosomal dominant. If they're enzyme disorders, you think autosomal recessive. Most of your inborn metabolic metabolism disorders are autosomal recessive. The American College of Obstetrics and Gynecology recommend offering cystic fibrosis carrier screening to all high-risk couples. In fact, probably the most common autosomal recessive disorder in Caucasian populations in the United States is cystic fibrosis. And here's our triad. Is the disorder transmitted by both genders? Does it skip generations? Are there male and female carriers? If there are, think autosomal recessive. All right, our third Mendelian disorder is X-linked recessive. And here is the pedigree here. Let's look at this. Does the disorder affect all generations? And you can see, no, it doesn't. It skips generations. Second question, are there carrier states? Yes, there are. Is there any gender predominance? And you notice the carriers are only females. The affected are only males. This is because it is carried on the X chromosome. Females have 2 X chromosomes, and so they can utilize the normal chromosome without having the disorder. Males are XY, they only have 1 chance. And if that X chromosome is affected, they're going to have the disorder. Examples are hemophilia, color blindness. It's very rare for a female to be colorblind. Hemophilia is one which has some interesting historical significance. No male-to-male transmission, because a father will only give his son his Y chromosome, so he cannot give the disorder. It is expressed only in males. There are female carriers. That is X-linked recessive. Queen Victoria, who lived from 1819 to 1901, was a carrier for hemophilia. In Europe at that time, royalty would not marry commoners. And so your selection of a mate was restricted to those who were of royalty only. So you had a limited genetic pool. This is Queen Victoria, and this is her consort, who was Prince Albert. He was of royalty as well. What is interesting is that Prince Albert here and Queen Victoria here had the same grandfather, consanguinity. His father and her mother were siblings. This is looking at the genetic line from Queen Victoria in current English royalty, Queen Victoria, Edward VIII, and so on. None of the current English monarchs have hemophilia. But if we look at the rest of the pedigree, we see that this is Queen Victoria, this is her daughter, and these are her granddaughters, and they were both carriers. And these are the affected children. And you can see how many of these. Some of these included the sons of the czars of Russia. And these kids, when they would fall down, which all kids do when they're playing, even from a minor fall, could develop significant bleeding until they could actually die. And Frederick William here died from a fall at age 2. That is X-linked recessive disorders. X-linked dominant disorders are even more rare. Now, as we look at the pedigree, you can see that it does not skip generations. Every generation is affected. You notice that both males and females can have the disorder. Notice that there are no carrier states, but what is interesting is mother can give it to daughter and to son, but father can only give it to daughters, cannot give it to the son. Examples of this, hypophosphatemic rickets, and many of these X-linked dominant disorders are lethal. And so those who would potentially pass it on to their children will die before they reach childbearing years. But this is your X-linked dominant. All right, we leave Mendelian disorders.